Hello everyone. In this video, we have to see about the lecture videos of crystal determination using X-ray diffraction techniques. Previous class, we have studied about the some of innovation about the X-ray diffraction. There is a laboratory that is William Conrogen is the inventor of that discovery of the X-rays. That will be honored with he will receive the Nobel Prize for this invention. It is this laboratory that is the first X-ray diagram. The X-ray photograph of this his wife is taken by this laboratory. So this is already we have known about the X-rays of electromagnetic waves whose wavelength about the 0.1 to 10 power minus 10 meters. So it was mainly X-rays are used in a medical diagnosis, but is the most of it is X-rays are most used in various fields, particularly in the determination of the crystal structure. The crystalline material and X-rays are very important for the identification of atoms into the particular orientation. Later on, that discovery of electrons diffraction by the crystals will be identified by the W. L. Van Loon. So he's he's the first man we have to discover the diffraction of the crystal. It will be the X-rays were exposed to the Na sodium chloride crystal and get the first diffraction patent. So it will be in a way break through that innovation about the X-ray diffraction that is called as a Bragg's law. Later on, W. H. Bragg's law and W. L. Lawrence Bloch, there is a father and son, have inverted the universal Bragg's law for diffraction of the X-ray crystal structure n lambda equal 2d sin theta. So it will be identify the position of atom into the particular crystalline material that will be used for identification of position of atoms, that will be used for the identification of position of atom. That is the how that position translation or what are the before class we have to say about the symmetry operations where the position will be atomic positions will be identified by this in diffraction techniques. So what happens, it will be the X-ray diffraction is nothing but it is the interference and the interference will be um, two interferences. The X-rays were scattered by this atom's position in the crystal. So the scattered lines and scattered waves can be interference one to another. So interference produces consecutive and distributive interference. So where the consecutive interference produces, that is called as a diffraction spot. That is a hot, dark and bright spots. So it will be uh, according to that polarity, according to the crystalline material, crystalline samples. So that is the next is the you can see that image of that X-rays on falling on a crystalline material. That is the arrow mark indicate that X-rays fall on a particular atoms that will be scattered along the overall the direction, that will be scattered into all the directions. So okay, second image you can see the incident beam on a particular point, that is the point means that is the atoms, it will scattered, that is creates a wave fronts. So one creates scattered and create wave fronts, another atom can fall in another electron, that is X-rays fall on another atom, that will be another position, that will be excited again it will scattered. So two of the wave fronts scattered from the two different atoms that will collide and interference and produce a diffraction point. That is the direction is called as a diffraction point. It is according to that number of electrons present in the crystal structure. Every atoms and molecules have a different numbers of electrons. So each electrons and atoms in the particular crystalline material can scatter all the electrons where that the Bragg's law satisfied, that only the diffraction spot get. So according to the electron density, that is called as a structure factor. The structure factor is nothing but number of electrons present is the structure factor is nothing but how much scattering factor, atomic scattering factor is nothing but how much of electrons density present in the crystal structure. According to that, electron diffraction can be possible. So more electron we can get the more complex more diffraction spots in the crystalline materials. So that is the complex of that atoms in the crystal structure. That is the scattered atoms, that is the mechanics of the pictorial of the wave complexity of that diffraction spot. You can see that mathematically having three different components. There is a wave has the different four components, that is a wavelength, phase and time period and phase shift. Phase and wavelength and frequency will be differed according to the time period. So every waves can be scattered, there is a shift in the phase. So according to the position and scattering atoms, so according to that we have to find out the using Fourier transform techniques, we have to find the structure factor calculation, that is by the formula. And then the position of atom, we have to define the position of the atom by Miller indices. So we can position that intercept of the Miller indices, we can use that Miller intercept included with that Fourier concept. We have to find the structure factor calculation. The structure factor is nothing but the possible of atoms in the particular position will be identified by these techniques. So these are, I can in this video I have stopped that basics of the structure factor calculation. Next we have to see about the next class we have to see about the deepest of this structure factor calculation, Fourier transforms, how involved in to calculate the structure factor of the atomic position of the atoms in the crystalline materials. Thank you.